Hello! In this video, we're going to look at some example problems on supremum of a set, infimum of a set, and bounded sets. So let's start off by reminding ourselves of some of the definitions. Let S be a subset of real numbers and let U be a real number. We say U is an upper bound of S if, for every x in S, x is less than or equal to U. So in other words, every element of S is less than or equal to U, or U is greater than or equal to every element of S. Next, the definition of a lower bound is, given S is a subset of real numbers and W is a real number, we say W is a lower bound of S if, for every x in S, x is greater than or equal to W. So what this is saying is, every element of S is greater than or equal to W, or W is less than or equal to every element of S. So now we have the definition of the supremum of a set and the definition of the infimum of a set. Starting with the definition of a supremum, let S be a subset of real numbers and let U be a real number. We say U is a supremum of S if U is an upper bound of S, and for every real number U prime, if U prime is an upper bound of S, then U is less than or equal to U prime. So, in other words, this second condition is saying U is less than or equal to every upper bound of S. So another name for the supremum of a set is the least upper bound of the set. So now we have the definition of the infimum of a set. Let S be a subset of real numbers and let W be a real number. We say W is an infimum of S if W is a lower bound of S, and for every real number W prime, if W prime is a lower bound of S, then W is greater than or equal to W prime. So in other words, this second condition is telling us that W is greater than or equal to every lower bound of S. So another name for the infimum of a set is the greatest lower bound of the set. Now it turns out, when a set has a supremum, then the supremum is unique, and we denote the supremum like this. When a set has an infimum, then the infimum is unique, and we denote the infimum like this. Now, I want to talk about a different way of formulating this second condition, and that is by using the contrapositive of this statement. The contrapositive of this tells us if U prime is less than U, then U prime is not an upper bound of S. Right? That's an equivalent way of putting this second condition. So now the definition of a supremum reads that U is an upper bound of S, and every real number less than U is not an upper bound of S. Right? So it still makes sense that U would be the least upper bound of S. Right? We could reformulate the second condition of the infimum of a set in the same way by using the contrapositive of this statement, which would tell us if W prime is greater than W, then W prime is not a lower bound of S. Right? So now the definition reads, W is a lower bound of S, and every real number bigger than W is not a lower bound of S. Right? So it still makes sense. W is the greatest lower bound of S. Right? So this is the definition of upper bound, lower bound, supremum, and infimum. Let's also remind ourselves of the definitions of a bounded set, and also what it means for a set to be bounded above and bounded below. Let S be a subset of the real numbers. We say S is bounded above if S has an upper bound. We say S is bounded below if S has a lower bound. And we say S is bounded if S is both bounded above and bounded below. Right? So in other words, S has both an upper bound and a lower bound. Now, an equivalent way of saying that a subset of real numbers is bounded, which is often useful, is the following. Let S be a subset of the real numbers. Then S is a bounded set if and only if there exists a positive real number, capital M, such that for every x in S, the absolute value of x is less than or equal to capital M. Right, so this will often be useful. Now, let's talk about the completeness property of the real numbers. This tells us that every non-empty subset of the real numbers that is bounded above has a supremum. So we're going to take this property as true. From this property, we have that every non-empty subset of real numbers that is bounded below must have an infimum. So that's often useful as well. And another fact that can be deduced from the completeness property of the real numbers is the Archimedean property, which tells us, given any real number x, there exists a positive integer n such that n is greater than x. And so this is often useful as well. So next, let's just remind ourselves of the definition of the maximum element of a set and the definition of the minimum element of a set before we start looking at some example problems. So let S be a subset of real numbers and let U be an element of S. We say U is a maximum of S if, for every x in S, x is less than or equal to U. So the maximum of a set is essentially an element of S and also an upper bound of S, right? That's another way of putting it. And also, the definition of minimum, let S be a subset of the real numbers and let W be an element of S. We say W is a minimum of S if for every x in S, x is greater than or equal to W, right? So another way of putting it is for W to be a minimum of S means that W is an element of S and W is a lower bound of S. Now, when a subset of real numbers has a maximum, then that maximum is unique. And we denote the maximum by this. When a subset of real numbers has a minimum, then the minimum is unique, and we denote the minimum like this. Now, it turns out, if a subset of real numbers has a maximum, then the maximum is the supremum of the set. If a subset of real numbers has a minimum, then the minimum is the supremum of the set. So these results are often useful as well. So now let's look at some example problems. Let S be the set of real numbers x such that x is greater than or equal to 0. Does S have a supremum? Does S have an infimum? If so, what are they? Prove your claims. So, this is the set of real numbers greater than or equal to 0, so you could visualize it, right? We have 0 right there, and then it extends forever to the right. So, does S have a supremum? Well, it doesn't seem like S would have any upper bounds, so can't have a supremum. So, no. Does S have an infimum? Well, it seems reasonable to claim that the infimum is 0, right? 0 is clearly going to be less than or equal to every element of the set, and 0 is going to be the greatest number that has that property, right? So our claim is that 0 is the infimum. And so let's try to prove those two facts. So we claim that S does not have a supremum. And so to show this, it's enough to show that S doesn't have an upper bound, right? Because if S has a supremum, then the supremum would be an upper bound, right? S doesn't have any upper bounds. So how do we show S doesn't have an upper bound? We're going to show for every real number U, U is not an upper bound of S. So let's consider an arbitrary real number U. From here, we're going to show that U is not an upper bound of S. So what does it mean for U to not be an upper bound of S? Well, for U to be an upper bound of S means that U is greater than or equal to every element of S. So then the negation of that means that U is strictly less than some element of S, right? So for U to not be an upper bound of S means U is strictly less than some element of S. That is what we want to prove. We want to prove U is strictly less than some element of S. Now, where is U? Well, we can imagine the number line, and we have 0 right here. And right here, this starting from 0 going forever to the right, that is our set S. We don't know where U is. U is an arbitrary real number. If U happens to belong to S, well then if we consider U plus 1, well U plus 1 is an element of S. And U is strictly less than U plus 1, so therefore U is strictly less than some element of S. So if U is an element of S, this is easy. So then we have to consider the possibility, well, what happens if U is not an element of S? Well, U plus 1 doesn't necessarily work, right? Because what if this is, say, -2? Then U plus 1 is going to be at -1, which is not an element of S, right? U plus 3 will work because it's an element of S, but how do we generalize this? How do we generalize this? Well, the trick is we don't have to split it up into cases like this. We can consider absolute values. No matter where U is, the absolute value of U will be greater than or equal to 0. If we add 1 to it, well, certainly U is strictly less than the absolute value of U plus 1. And the absolute value of U plus 1 is an element of S because it's greater than or equal to 0. So that's the idea. We consider absolute value of U plus 1. First of all, we should show absolute value of U plus 1 is an element of S. So I'm going to say note that absolute value of U plus 1 is greater than absolute value of U. And absolute value of any real number is greater than or equal to 0. So this is greater than or equal to 0. So this shows absolute value of U plus 1 is greater than or equal to 0. So absolute value of U plus 1 is an element of S. But U is strictly less than this quantity, right? So I'm going to say, and also, U is less than or equal to the absolute value of U, right? Every real number is less than or equal to its absolute value, right? So then we know absolute value of U is strictly less than absolute value of U plus 1. So this shows U is strictly less than absolute value of U plus 1. So what we see here is U is strictly less than some element in S. And that's precisely what it means for U to not be an upper bound of S. Because U is not an upper bound of S, U can't be a supremum of S, right? And so we're done. We have shown if U is any real number, then U is not a supremum of S. Therefore, every real number is not a supremum of S, so we conclude S does not have a supremum. And so that's it for supremum. What about infimum? Our claim is that the infimum of S is equal to 0. Now to show this, we can show that 0 is the smallest element of S, right? So we're going to be using that result that we mentioned before we got into this example problem. So first off, we know that 0 is an element of S because 0 is greater than or equal to 0. So for 0 to be the smallest element of S, we need 0 to be an element of S itself. We also need, for every x in S, x is greater than or equal to 0, right? By definition of smallest element, or minimum element. So to prove that, let's give ourselves an arbitrary x in S. Well then by definition, x is greater than or equal to 0, right? By definition of S. So since x was an arbitrary element of S, this shows for all x in S, x is greater than or equal to 0. And so since 0 is an element of S, and for all x in S, x is greater than or equal to 0, by definition, 0 is the minimum of S. But remember, when a set has a minimum, the minimum is the infimum. So this implies the infimum of S is equal to 0. And so that's it. That proves our claim of the infimum. So this is it for this example problem. Now we're going to look at a slightly modified version of this. And that is, we are going to consider the set of real numbers that are strictly greater than 0. So let S be the set of real numbers strictly greater than 0. Does S have a supremum? Does S have an infimum? If so, what are they? Prove your claims. So first off, if we just visualize this graph, or visualize this set, it looks something like this. Right here we have 0, and then the set extends forever to the right. So does S have a supremum? Well, since it extends forever to the right, it shouldn't have any upper bound, so our claim is that it does not have a supremum. Does S have an infimum? Our claim is again going to be that the infimum of S is equal to 0. But notice, 0 is not actually an element of the set. So proving that 0 is the infimum, we'll have to do it a different way than we did before. So now let's get into proving our claims. So our claim is that S does not have a supremum. And to show that, we're going to show that S does not have an upper bound. So to do that, we're going to show for every real number U is not an upper bound of S. Or actually, for every real number U is not a supremum of S. Right? So we're going to give ourselves an arbitrary real number U, and we're going to end up arriving at the fact that U is not an upper bound of S, and therefore U is not a supremum of S. Right? So we can essentially do the same argument that we did in the previous example. Right? We consider absolute value of U plus 1, because we know that absolute value of U plus 1 is going to be strictly greater than 0. So we can pretty much write the same sort of thing that we did before. So note, the absolute value of U plus 1 is strictly greater than absolute value of U, right? Because we're adding 1 here. Here we're not adding 1, right? 1 is greater than 0, therefore absolute value of U plus 1 is greater than absolute value of U plus 0, right? That's really where that's coming from. So then the absolute value of any real number is greater than or equal to 0. So absolute value of U is greater than or equal to 0. So this tells us absolute value of U plus 1 must be strictly greater than 0. And so absolute value of U plus 1 is a real number greater than 0, so it satisfies the condition to be an element of S. And so absolute value of U plus 1 is an element of S. But then once again, we can show U is strictly less than absolute value of U plus 1. Also note, right, that's so I'm going to write also note, U is less than or equal to the absolute value of U, right? Every real number is less than or equal to its absolute value. But then absolute value of U is strictly less than the absolute value of U plus 1, because we added 1. So this shows U is strictly less than absolute value of U plus 1. So putting this all together, we see that U is strictly less than some element in S. Therefore, U is not an upper bound of S. And so, because U is not an upper bound of S, U can't be the supremum of S. So we see, putting this all together now, given an arbitrary real number U, it follows that U is not a supremum of S. Therefore, every real number is not a supremum of S, so S does not have a supremum. So that's it. That proves our claim about a supremum. Now we're going to prove the infimum is 0. But again, we can't do this the way we did in the previous example, because 0 is not going to be the smallest element of S, right? Because 0 isn't even an element of S. So to do this, well, we're going to go from the definition of the infimum. To show that the infimum of S is equal to 0, we first want to show that 0 is itself a lower bound of S. So first, that's the first thing we want to show. We want to show 0 is a lower bound of S. To prove that 0 is a lower bound of S, we want to prove for every x in S, x is greater than or equal to 0. Right? That's from the definition of a lower bound. So let's give ourselves an arbitrary x in S. Well, then by definition of S, this means x is a real number such that x is greater than 0. So by definition of S, we have x is greater than 0. But since x is greater than 0, that means x is greater than or equal to 0. So now, since x is an arbitrary element of S, this proves for all x in S, x is greater than or equal to 0. That's precisely what it means for 0 to be a lower bound of S. So that's the first condition for 0 to be the infimum of S. We now want to show that 0 is the greatest lower bound of S, right? We want to prove that second condition. And one way of proving that second condition for the infimum is to prove anything greater than 0 is not a lower bound of S. So let's give ourselves an arbitrary real number w prime greater than 0. From here, we want to show w prime is not a lower bound of S. That will verify the second condition for 0 to be the infimum of S. Well, then from here, if we take half of w prime, then we see w prime is greater than w prime over 2, which is greater than 0. Now, since w prime over 2 is greater than 0, we know that w prime over 2 is an element of S by definition. And now putting this all together, we see that w prime is strictly greater than some element in S. And that is what it means for w prime to not be a lower bound of S. So putting this all together, we see, given any real number w prime greater than 0, it follows that w prime is not a lower bound of S. So this proves every real number greater than 0 is not a lower bound of S. So since we've shown 0 is a lower bound of S, and anything bigger than 0 is not a lower bound of S, that means 0 must be the infimum of S by definition. And so we're done. So this is it for this example problem. Now let's look at another one. So for this example, let S be the set of real numbers of the form 1 over n, where n is a positive integer. Does S have a supremum? Does S have an infimum? If so, what are they? Prove your claims. So if we just visualize what this set looks like, we have 1, then 1/2, and 1/3, 1/4, and so on. It seems like we're going to get really close to 0. But 0 isn't an element of the set, right? 0 is definitely less than or equal to every element of the set. In fact, 0 is less than every element of the set. So 0 is going to be a lower bound of the set, but it seems reasonable to claim 0 is going to be the infimum of the set, right? If we consider anything bigger than 0, well, we should be able to find an element of the set less than it, right? If you consider anything bigger than 0, you'll end up if you basically travel anywhere further from 0 to the right on the number line, you should immediately pass some element of S, essentially, right? It seems reasonable to claim that 0 is the infimum of S. As for the supremum, it seems like 1 is the largest element of the set, so we should show the supremum is equal to 1. So now let's get into proving our claims, starting with the supremum. So to show the supremum of S is equal to 1, we just have to show that 1 is the largest element of S. To show that 1 is the largest element of S, or the maximum of S, first we show 1 is an element of S. Well, we know that 1 is an element of S, since 1 is equal to 1 over 1, and 1 is a positive integer. Well then, 1 is an element of S. Right? 1 can be written in the form 1 over n for some positive integer n. Just take n to be 1. 1 is an element of S. But now, to see that 1 is the largest element of S, we want to show for every x in S, x is less than or equal to 1. So let's give ourselves an arbitrary element, x and s. Well then, by definition of s, for x to be an element of s means that x is equal to 1 over n for some positive integer n. So we're essentially trying to show that 1 over n is less than or equal to 1. Well, since n is a positive integer, we know that n is greater than or equal to 1. Every positive integer is greater than or equal to 1. Now, there's a property about positive numbers that tells us if we have two positive numbers in an inequality, if we take the reciprocal of both of them, it will flip the sign of the inequality. So, if taking the reciprocal of these guys, we get 1 over n is less than or equal to 1. So, 1 over n is less than or equal to 1. And so, x is less than or equal to 1. That's it. So, we see, given an arbitrary element x and s, x is less than or equal to 1. So we have proven for all x and s, x is less than or equal to 1. So, since 1 is an element of s, and every element of s is less than or equal to 1, that means 1 is the largest element of s. So we'll write max of s equals 1. But if a set has a maximum, then the maximum is the supremum. So that tells us 1 is the supremum of s. And so we're done. This proves our claim about the supremum. Now let's prove our claim about the infimum. Now to prove the infimum of s is equal to 0, we're going to invoke the Archimedean property. So, first off, to show that the infimum of s is equal to 0, by definition of the infimum of a set, we want to show that 0 is a lower bound of s. To show that 0 is a lower bound of s, we want to show for every x and s, x is greater than or equal to 0. So let's give ourselves an arbitrary x and s. In fact, just to keep things a little bit maybe less confusing, instead of using x, I'm going to call it y, because we already used x up here. So I'm going to say let y and s be arbitrary. Then y has the form 1 over m for some positive integer m. Instead of calling it the letter n, I'm going to say 1 over m, right, for some positive integer m. Now, there's a property about fractions, or basically it's a property of this notation. Since since m is a positive integer, m is greater than 0. The reciprocal of any positive number is positive. So since m is positive, 1 over m is positive. Now I'm going to say since m is a positive integer, that tells us m is greater than 0. So 1 over m is greater than 0, and hence y is greater than 0. But since y is greater than 0, we can say y is greater than or equal to 0. So this shows if y is any element of s, then y is greater than or equal to 0. And therefore, for all y in s, y is greater than or equal to 0. And that's precisely what it means for 0 to be a lower bound of s. So now we want to show 0 is the infimum of s, right? The property what makes it the greatest lower bound of s, right? We wanted to prove that second property of the infimum of a set. And remember from our from what we were doing at the beginning of this example, we are thinking about 0, but then if we go anywhere, if we walk anywhere to the right, doesn't matter how much distance you walk, but you walk any amount of distance to the right, you will immediately encounter some element of s, was our claim. So the idea is, we're going to show for every real number, w prime, if w prime is greater than 0, then w prime is not a lower bound of s, right? So we're going to use that version of the second part of the definition of the infimum. So let's let w prime be a real number greater than 0. We want to show w prime is not a lower bound of s. In other words, we want to show that w prime is strictly bigger than some element of s. Now, to show that, we're going to essentially end up with something like w prime is greater than 1 over p, where p is some positive integer. Now, when we come up with this, well, this is equivalent to if we have p greater than 1 over w prime, right? It's equivalent to saying p is a positive integer bigger than 1 over w prime. And this is how we invoke the Archimedean property. Since 1 over w prime is a real number, there must exist some positive integer bigger than it. And so we call that positive integer p. That is how we invoke the Archimedean property. So just like that. But then, since p is positive and w prime is positive, we can divide p to the other side, multiply w prime to the other side, and so we get w prime is greater than 1 over p, but 1 over p is an element of S, right? It fits the form 1 over n, where n is a positive integer. Just take n to be p. So this is an element of S. We see that w prime is strictly bigger than some element in S. Therefore, w prime is not a lower bound of S. And so that verifies the second condition for 0 to be the infimum of S. So this proves the infimum of S is equal to 0. And so we're done. This completes this example problem. So next, let's look at our next example problem. Let S be the set of real numbers of the form 1 minus negative 1 to the power of n over n, where n is some positive integer. Does S have a supremum? Does S have an infimum? If so, what are they? Prove your claims. So we know that when we vary n, negative 1 to the power of n is going to alternate between 1 and negative 1. So maybe if we write down the elements of the set, we get an idea of what's going on. So starting from n equals 1, n equals 2, n equals 3, and so on, the elements of the set are as follows. We see that we have 2, 1/2, 4/3, 3/4, 6/5, 5/6, and so on. So then if we compare, I'm just going to circle every other one just so we can see sort of what's going on here. So essentially, it seems that if we look at the uncircled sequence, we have 1/2, 3/4, 5/6, and this sequence is always increasing. Basically increasing closer and closer to 1, it seems, while the circled sequence, that seems to be decreasing closer and closer to 1. So it seems like our set has a maximum and a minimum. So proving the infimum and supremum shouldn't be too difficult. We just have to prove that this guy's the maximum, this guy's the minimum. So our claim is that the supremum is going to be 2, the infimum is going to be 1/2. And so we just have to prove that this is the maximum, this is the minimum in order to show that. First of all, to show that 2 is the maximum of S, we need to show 2 is an element of S. Well, if we plug in n for 1, we're going to say note 2 is equal to 1 minus negative 1 to the power of 1 over 1, right? Because this is just negative 1 over 1, so it's 1 minus negative 1, just 2. This is an element of S because it fits the form. So 2 is an element of S, but why is 2 going to be the largest element of S? To prove that, well, we want to show for every x in S, x is less than or equal to 2. So to do that, let's give ourselves an arbitrary element, x in S. Now to show x is less than or equal to 2, from what we observed about the behavior of the sequence, we saw that one portion was decreasing to 1, while another portion was increasing to 1, as it appeared. So it might be useful if we split this up into cases, right? So before we do that, actually, since x is an element of S, that means x has this form. So x is equal to 1 minus negative 1 to the power of n over n for some positive integer n. And now, to show x is less than or equal to 2, it might be useful to split this up into cases. Right? In this case, depending on whether n is even or odd, right? Because it depends on whether we get 1 or negative 1. We could also just say whether n is even or odd, we know negative 1 to the power of n is going to be equal to 1 or negative 1. So I'm going to just actually say, note negative 1 to the power of n is equal to 1, or negative 1 to the power of n is equal to negative 1. So we could go from there. And so splitting this up into cases, we consider case 1, negative 1 to the power of n is equal to 1. Well then, x is equal to 1 minus 1 over n. This is less than 1, right? Because we're subtracting a positive number. So this is less than 1, which is less than 2. So x is less than 2, so x is less than or equal to 2. That completes case 1. As for case 2, negative 1 to the power of n is equal to negative 1. Well then in that case, x is equal to 1 minus negative 1 over n, which is equal to 1 plus 1 over n. But now we need to make the observation that 1 over n is less than or equal to 1. Just like we did in the previous example, right? So, since n is a positive integer, we know that n is greater than or equal to 1. And since n is greater than or equal to 1, these guys are both positive. So if we take the reciprocal of both of them, that flips the sign of the inequality. We get to 1 over n less than or equal to 1. And so we see if we add 1 on both sides, we get 1 plus 1 over n is less than or equal to 2. And so x is equal to 1 plus 1 over n. That's less than or equal to 1 plus 1, right? All we've done here is we added 1 to both sides of this inequality. We get this. That's equal to 2. So x is less than or equal to 2. So in either case, we see x is less than or equal to 2. So putting this all together, we have shown for every x in S, x is less than or equal to 2. And so that proves 2 is the largest element of S, right? Because 2 is an element of S itself, and every element of S is less than or equal to 2. Therefore, 2 is the maximum element of S. But the maximum of a set is the supremum, so this shows the supremum of S is equal to 2. And so we're done. That proves our claim about the supremum. Now let's prove our claim about the infimum. And just so I have enough room, I'm going to move back up to the top. So to show the infimum of S is equal to 1/2, we're going to show that 1/2 is the smallest element of S. First off, we need to show that 1/2 is an element of S itself. Well, if we just plug in n for 2, we see that 1/2 will be equal to 1 minus negative 1 squared over 2, right? That's equal to 1/2. And since this fits the form to be an element of S, it must be an element of S. So 1/2 is an element of S. Now we want to show that every element of S is greater than or equal to 1/2. That will prove 1/2 is the smallest element of S. So to do that, we give ourselves an arbitrary element of S. I'll call it y. Well then, y fits the form 1 minus negative 1 to the power of m over m for some positive integer n. Now to show y is greater than or equal to 1/2, just like we did for the supremum, we're going to split this up into two cases once again, depending on whether negative 1 to the power of m is equal to 1 or whether it's equal to negative 1. And so, from here, we're going to show in either case, y is greater than or equal to 1/2. We'll start with the case that negative 1 to the power of m is equal to 1. Well then, y is equal to 1 minus 1 over m, so 1 minus 1 over m. Now, how do we show 1 over m? How do we show that this quantity is greater than or equal to 1/2? Well, for this quantity to be greater than or equal to 1/2, this happens exactly when 1 over m is less than or equal to 1/2. Right? If we just manipulate this, add the 1 over m to the other side, subtract the 1/2 to the other side, this happens exactly when 1 over m is less than or equal to 1/2. But since we're dealing with a positive number m and a positive number 2. If we take the reciprocal of these two guys, this happens exactly when m is greater than or equal to 2. So all we have to do here is show that m is not equal to 1, right? Since m is a positive integer, m is greater than or equal to 1. So if we show m is not equal to 1, that implies m is greater than or equal to 2, which implies this quantity is greater than or equal to 1/2, which implies y is greater than or equal to 1/2, which is what we want. So here's what we do. Why can't y be equal to, why can't m be equal to 1? If m is equal to 1, then -1 to the power of m is equal to -1, which is, that's not what it is. 1 is not equal to -1, so this contradicts that -1 to the power of m is equal to -1. Thus, m is greater than or equal to 2. And now we can follow from here to here to here. So since m is greater than or equal to 2, we have 1 over m less than or equal to 1/2. So then from here, we should obtain 1 minus 1 over m is greater than or equal to 1/2. Right? You could obtain that by negating both sides and then adding 1 on both sides. And so we get 1 minus 1 over m is greater than or equal to 1/2. And that tells us y is greater than or equal to 1/2. And so we're done. This completes case 1. Now let's move on to case 2, where -1 to the power of m is equal to -1. Well then, in this case, y is equal to 1 minus -1 over m. And that's the same thing as 1 plus 1 over m. And we know 1 over m is greater than 0, so this is greater than 1. 1 is greater than 1/2. So that's it. Y is greater than 1/2, so y is greater than or equal to 1/2. This case was much easier than the previous case. So that's it. We see, given any element y in S, it follows y is greater than or equal to 1/2. So for all y in S, y is greater than or equal to 1/2. Right, so putting this all together, we have shown 1/2 is an element of S, and every element of S is greater than or equal to 1/2. Therefore, 1/2 is the smallest element of S. And so the infimum of S is equal to 1/2. And so that's it. That proves our claim about the infimum. And so that's pretty much it for this example problem. Let S be the set of non-zero real numbers such that x is less than 1 over x. Does S have a supremum? Does S have an infimum? If so, what are they? Prove your claims. So, let's think about what the set looks like. So, if we consider an arbitrary non-zero real number in this set, we have x less than 1 over x. Now, you might be thinking, let's try and multiply x on both sides of this inequality and see what happens. Well, depending on whether x is positive or negative, the sign of the inequality will either flip or not flip. So let's split this up into cases. What happens if x is positive? Well, then when we multiply x on both sides of this inequality, we get x squared is less than 1. Now, when x is positive, this happens exactly when x lies between 0 and 1. Okay, so that's what this set looks like when x is positive. It should be the set of real numbers x between 0 and 1. So then what happens when x is less than 0? Well, then when we multiply x on both sides of this inequality, we get x squared and 1, but the sign of the inequality flips. We get x squared is greater than 1. And as long as x is less than 0, well, then this happens exactly when x is less than -1. Right? If you just visualize the graph of y equals x squared, when x is positive and x squared is less than 1, that happens exactly when this happens. Right? Again, visualizing the graph of y equals x squared, this and this happen exactly when this happens. So, from what we see here, it seems that S should be precisely the set of real numbers x between 0 and 1 unioned with the set of real numbers x less than -1. And so, if we prove that first, that might make it easier to basically find the supremum and the infimum. It might. So let's just do that first. So writing it in interval notation, we're trying to show S is equal to the union of these two intervals, right? Now, making a claim about the supremum and infimum of this set is probably a little bit easier. So the supremum we expect to be at 1. The infimum, well, since this set extends forever downward, we don't expect the infimum to exist. So we're first going to show S is the union of these two intervals. So we're trying to prove two sets are equal. So we're going to show S is a subset of this set, and we're going to show this set is a subset of S. To show that S is a subset of this set, let's give ourselves an arbitrary element of X, or arbitrary element of S. I'll call it X. Well, then this means X is non-zero, X is less than 1 over X. Now to show X is an element of the union of these two intervals, we split it up into two cases. Either X is greater than 0 or X is less than 0. We'll start with the first case. Start with the case X is greater than 0. Well then, if we take this inequality, multiply X on both sides, sign of the inequality remains the same, we get X squared less than 1. Now the claim is, since X is greater than 0, our claim is X lies between 0 and 1. We know X is greater than 0, all we have to do is show that X is less than 1. And so one way that we could do that is by taking the square root of both sides, right? That works because you would get X, the square root of X squared less than square root of 1, so then X is less than 1. Alternatively, you could subtract the 1 over to the other side. You get X minus 1 times X plus 1. That's equal to X squared minus 1, so that's less than 0. Since X is greater than 0, X plus 1 is greater than 0. So what does that allow us to do? Well, we could divide X plus 1 on both sides. We get X minus 1 is less than 0. X minus 1 is less than 0, and so X is less than 1. Thus, X lies in 0, 1. So that completes the case where X is greater than 0. Right? We've shown X lies in this set. Now let's consider the case X is less than 0. So case 2, X is less than 0. Well then, when we multiply X on both sides of this inequality, sign of the inequality flips. So we get X squared greater than 1. Now, you could do this by taking the square root of both sides. If you do that, you have square root of X squared greater than square root of 1, right? That will be true. This is 1, but what is the square root of X squared? It is always equal to the absolute value of X. Always. So then, since X is less than 0, absolute value of X is equal to negative X in this case. You get negative X is greater than 1, and hence X is less than negative 1. X is less than negative 1, so that's exactly what we want. It belongs to this interval. Right, so you could do it that way, that works. I'm just going to do it a different way though, because why not, right? So again, we're going to subtract 1 to the other side. We get X minus 1 times X plus 1, that's X squared minus 1. You subtract 1 to the other side, that's greater than 0. So now, since X is less than 0, that means X minus 1 must be less than 0. Right, so since X is less than 0, X minus 1 is less than 0. So if we divide X minus 1 on both sides of this inequality, that flips the sign of the inequality. We're left with X plus 1 is less than 0. So that happens, then subtracting 1 to the other side, we get X is less than negative 1. Thus, X lies in the interval negative infinity, comma negative 1. And so that's it. In either case, we see x must belong to the union of these two intervals. So putting this all together, we see if x is an arbitrary element of S, then x must belong to the union of these intervals, and therefore S is a subset of the union of these two intervals. So now we're going to show that the union of these two intervals is a subset of X. To do that, let's give ourselves an arbitrary element of the union of these intervals, call it Y. Well then, we're going to show Y is an element of S. Again, we're going to split this up into two cases. Either Y is an element of this interval or Y is an element of this interval. In either case, we'll show that Y is an element of S. So we'll start with case 1. Y is an element of this interval. Well then, we see Y is less than -1. We want to show, right? We know Y is non-zero, so Y automatically satisfies this condition. We want to show Y is less than 1 over Y. Well, to do that, how do we do that? Well, we're going to multiply Y on both sides of this inequality. So what does that do? Y is negative, so that flips the sign of the inequality. So we get Y squared is greater than -Y. So then, what about -Y? Well, if we negate both sides of this inequality, we get -Y is greater than 1. So this shows Y squared is greater than 1. So now we divide Y on both sides of this inequality. That gives us Y is less than 1 over Y. Right? Flips the sign of the inequality since Y is negative. So we see Y is a non-zero real number such that Y is less than 1 over Y, so Y is an element of S. So that completes case 1. Now we move on to case 2, where Y is an element of 0, 1. Well then, Y lies between 0 and 1, so automatically Y is non-zero. So all that's left to show is Y is less than 1 over Y. Well, since Y is less than 1, and we multiply the positive number Y on both sides of Y less than 1, we get Y squared is less than Y. So Y squared is less than Y, and Y is less than 1. So this shows Y squared is less than 1. Right? So Y squared is less than 1. And dividing the positive number Y on both sides of this inequality, we get Y is less than 1 over Y. Thus, Y is an element of S. So that's it. In either case, we deduce that Y is an element of S. So for every Y in the union of these two intervals, it follows that Y is an element of S. So the union of these two intervals is a subset of S. And hence, because we have shown that S is a subset of the union of the intervals of the intervals is a subset of S, therefore they must be equal. So that's it. That proves that S is precisely the union of these intervals. So now we're going to show that the supremum of the set is 1, the infimum of the set does not exist. So we claim that the supremum of S is equal to 1. Now notice 1 is not an element of S. So we'll have to prove this from the definition. Well, maybe we don't have to, but we're going to prove that 1 is the supremum of S from the definition of the supremum. So, from the definition of the supremum, we first want to show 1 is an upper bound of S. To do that, we're trying to show for every x in S, x is less than or equal to 1. So let's give ourselves an arbitrary x in S. From here, we want to show x is less than or equal to 1. To do that, we could split this up into two cases. Either x is an element of this interval, or x is an element of this interval. So, let's start with case 1. Suppose x is an element of this interval. Well then, x is less than -1, -1 is less than 1, so this shows x is less than 1, and so x is less than or equal to 1. So that completes case 1. As for case 2, we consider what happens if x is an element of the other interval, if x is an element of 0, 1. By definition of this interval, this means x lies between 0 and 1. So we see x is less than 1, and so x is less than or equal to 1. And so that's it. No matter what, x is less than or equal to 1. So this shows, given any element x and s, we have x is less than or equal to 1. Thus, for all x and s, x is less than or equal to 1. And that's precisely what it means for 1 to be an upper bound of s. Now we want to show 1 is the least upper bound of s, right? So we want to verify that second condition for the supremum, right? And to do that, well, we're going to do it the way we've been doing it. We're going to prove, well, basically we're going to do it the way where we give ourselves an arbitrary real number, u prime, less than 1, and prove that u prime is not an upper bound of s. So we're going to prove any real number less than 1 is not an upper bound of s. Right? That's a way that we can verify that second condition. So let's give ourselves an arbitrary real number, u prime less than 1. From here, we're going to show that u prime is not an upper bound of s. So here's the thing. Where is u prime? Well, if we consider where u prime is with respect to s, well, s is essentially the union of these two intervals. So we have the left half right here and the right half like this. U prime is just some real number less than 1. So if we split this up into cases, one possibility is that u prime lies somewhere in this interval. In that case, we can choose a real number to the right of it between 0 and 1. That number will have to be an element of 0, 1. So u prime is strictly less than some element of s. Therefore, u prime is not an upper bound of s. So that completes the case if u prime actually lied in this interval. But if u prime doesn't lie in the interval, then as you can imagine, it would be somewhere to the left of this interval. But then we just choose any element of this interval, u prime would be strictly less than that element in the interval. So u prime is strictly less than some element of s. So really we're going to split it up into cases that way. Exactly, we're going to do it slightly differently, but it's the same idea. If we consider 1/2, either u prime is less than 1/2 or u prime is greater than or equal to 1/2. Right? If u prime is less than 1/2, then u prime is strictly less than some element of s, namely 1/2. Otherwise, if u prime is greater than or equal to 1/2, u prime lies somewhere in here. So then if we consider the average of u prime and 1, the average of u prime and 1 lies in this interval. U prime is strictly less than the average of u prime and 1. So u prime is strictly less than some element of s. So we're going to split it up into cases that way. We first start with the case u prime is less than 1/2. Well, since 1/2 lies between 0 and 1, basically 1/2 lies in s. So u prime is strictly less than some element of s. So u prime is not an upper bound of s. So we immediately get the conclusion if u prime is less than 1/2. For our second case, u prime is greater than or equal to 1/2. Well then, what we can do here is 0 is less than 1/2. 1/2 is less than or equal to u prime. But here's the thing, u prime is less than 1. So the average of u prime and 1, right, u prime plus 1 over 2, strictly between u prime and 1. So what this shows here is that u prime plus 1 over 2 lies strictly between 0 and 1. So u prime plus 1 over 2 is an element of 0, 1, which means u prime plus 1 over 2 is an element of s. U prime is strictly less than some element in s, and therefore u prime is not an upper bound of s. And so, in either case, we have shown u prime is not an upper bound of s. So this shows if u prime is any real number that is less than 1, u prime is not an upper bound of s. So, putting this all together, we have shown 1 is an upper bound of s, and anything less than 1 is not an upper bound of s. That proves 1 is the supremum of s by definition. And so that proves our claim about the supremum. Now let's prove our claim about the infimum. We claim S does not have an infimum. And to do that, we just gotta show S doesn't have a lower bound, right? Basically, that's what we're going to end up demonstrating here. So we're gonna show, given an arbitrary real number W, W is not an infimum of S, right? So let W be an arbitrary real number. From here, we're gonna show W is not a lower bound of S, and therefore W is not an infimum of S. So, since W is a real number, well, we essentially just have to pick some element in negative infinity comma negative 1 that is less than W. Now, if W was less than negative 1, then W minus 1 would work. But if W is, say, like 100, then W isn't even close to negative infinity comma negative 1. We would need like W minus 200, right? Something like that. But if we recall, from the first two examples that we did in this video, instead of splitting it up into the cases, we could take advantage of the absolute value of W, right? If we consider the negative of the absolute value W, that's less than or equal to 0. Subtract 1, that's less than or equal to negative 1. So then if we just subtract 2, that's less than negative 1. And that's clearly less than W. Right, we can show that. So this is essentially what we're going to take advantage of. So to show W is not a lower bound of S, we want to show that W is strictly bigger than some element of S, basically. Right, W is strictly bigger than negative absolute value W minus 2. And this quantity belongs to this interval, which is an element of S. W is strictly bigger than some element of S, right? So that's essentially what we're going to end up showing here. So here's the idea. Note that the absolute value W is greater than or equal to 0. So negative absolute value W is less than or equal to 0. And so when we subtract 2 on both sides, we get negative absolute value W minus 2 less than or equal to negative 2, which is less than negative 1. So we see that the negative of the absolute value W minus 2 less than negative 1, so it's an element of negative infinity comma negative 1, which is a subset of S. So negative absolute value W minus 2 is an element of S. Now we want to show W is strictly bigger than this element of S. Well, this comes from the fact that W is less than or equal to the absolute value of W. Actually, it doesn't, well, maybe it does, but instead, there's a fact about absolute values which tells us for any real number A, so if A is any real number, then A lies between the negative of absolute value of A and the absolute value of A. So we're taking advantage of this fact. So in this case, we note that W is greater than or equal to the negative absolute value of W. Right? That comes from what we have here. Taking A to W, W is greater than or equal to negative absolute value of W. So that's what we get here. But when we subtract 2, this is going to be strictly bigger than negative absolute value of W minus 2. So W is strictly bigger than negative absolute value of W minus 2. So what we see here is W is strictly bigger than some element which lies in S. So W is not a lower bound of S. And therefore W can't be an infimum of S. So since W was an arbitrary real number, this shows that every real number is not an infimum of S. So S does not have an infimum. And so that is it for this example. Let S be the set of all real numbers of the form 1 over n minus 1 over m, where n and m are positive integers. Does S have a supremum? If so, what is it? Prove your claim. Now, one way of thinking about what the supremum of S is by trying to make 1 over n as large as possible and make 1 over m as small as possible. Now, to make 1 over n as large as possible, we're trying to make n as small as possible. So we just take n to be 1. We get 1 over 1. As for the second term, 1 over m, to make it as small as possible, we make m as large as possible. So then the second term essentially becomes 0, because when we take m really, really, really large, 1 over m essentially becomes 0, right? But this is just equal to 1. So the supremum of this set should just be 1, and we're going to show that. Now to show this, we're going to go from the definition of the supremum. We're first going to show 1 is an upper bound of S. To show that, let's give ourselves an arbitrary element, x in S. From here, we're going to show x is less than or equal to 1. Now, since x is an element of S, this means that x is equal to 1 over n minus 1 over m for some positive integers n and n. Now, we're trying to show that this quantity is less than or equal to 1. And the idea is 1 over n should be less than or equal to 1, but then we're taking that and subtracting a positive value, which makes it even smaller. So it's going to be less than 1. So the idea is, since n is a positive integer, we know n is greater than or equal to 1. So then taking the reciprocal of both of these guys, we get 1 over n is less than or equal to 1. Right, but then the idea is we subtract 1 over m, which is positive. So when we subtract a positive number, that makes this guy even smaller, making it less than 1. So we're going to show 1 over m is greater than 0. So the idea is, since m is a positive integer, we know positive integers are positive, right? We have m greater than 0, so then the reciprocal of m must be greater than 0. So 1 over m is greater than 0. Thus, when we negate both sides, negative 1 over m is less than 0. So when we add 1 over n on both sides, we get to 1 over n minus 1 over m is less than 1 over n. This is x, and 1 over n is less than or equal to 1. So this shows x is less than or equal to 1. And so we're done. We see, given arbitrary x and s, it follows that x is less than or equal to 1. So for all x and s, x is less than or equal to 1. That's precisely what it means for 1 to be an upper bound of S. Now we're going to show 1 is the least upper bound of S. So, what does that mean? We want to show, given any real number u prime less than 1, u prime is not an upper bound of S, right? That's the way we're going to do it, like we've been doing it. So, let's give ourselves an arbitrary real number, u prime less than 1. From here, we want to show u prime is not an upper bound of S. So how do we do that? As you may have guessed, we somehow need to invoke the Archimedean property, right? So to show u prime is not an upper bound of S, we're trying to show u prime is strictly less than some element of the set. Now it makes sense. When we walk anywhere to the left of 1, we should encounter some real number of the form 1 minus 1 over p immediately, where p is some positive integer, right? It doesn't matter how much distance you walk to the left of 1. If you walk any amount of distance to the left of 1, you should immediately encounter some real number of this form. But 1 minus 1 over p is an element of S, because 1 can be written as 1 over 1, right? This is just 1 over 1. So 1 over 1 minus 1 over p fits the form to be an element of S. just take n to be 1, m to be p. It must be an element of S. So the idea is we can show u prime is less than 1 minus 1 over p, where p is some positive integer. And to see how, well, if we take this inequality and solve for p, what do we get? Well, I'm just solving for p. We get that p would have to be greater than 1 over 1 minus u prime. So we just invoke the Archimedean property by choosing some positive integer p bigger than 1 over 1 minus u prime. But then, in what I just erased, we should be able to obtain u prime is less than 1 minus 1 over p. So what we see here, if we do that, we can multiply 1 minus u prime to the other side, divide p to the other side. Since both of them are positive, the sign of the inequality will remain the same. So 1 minus u prime is greater than 1 over p. So adding u prime to the other side, subtracting 1 over p to the other side, we get u prime is less than 1 minus 1 over p. Right? We note this is the same thing as 1 over 1 minus 1 over p. So it fits the form to be an element of S. Right? So it's an element of S. What we see here is that u is strictly less than some element in S. Which means u prime is not an upper bound of S. Right? If u prime was an upper bound of S, u prime would be greater than or equal to every element of S. But no, u prime is strictly less than some element in S, which means u prime is not an upper bound of S. So this shows if u prime is any real number less than 1, then u prime is not an upper bound of S. And that was the second condition for 1 to be the supremum of S. So we're done. We've proven that the supremum of S is equal to 1. So that's it. That completes this example problem. Let A and B be non-empty subsets of real numbers that are bounded above. Prove that the supremum of the union of A and B is equal to the maximum of supremum of A and the supremum of B. Now, since A and B are non-empty and bounded above, well then by the completeness property of the real numbers, the existence of the supremum of A and the supremum of B makes sense. So now we want to show that the union of A and B, we want to show that the supremum of the union of A and B is the maximum of the supremum of A and supremum of B. And we'll show that according to the definition of the supremum. So, to prove this, let's, for convenience, call this value capital N. So, to show that M is the supremum of the union of A and B, we want to show first that M is an upper bound of the union of A and B. To show that, we want to show for every x in the union of A and B, x is less than or equal to M. So let's give ourselves an arbitrary x in the union of A and B. From here, we're going to show x is less than or equal to M. From here, it's almost natural to split it up into cases. Either x is an element of A or x is an element of B. So let's start with the case x is an element of A. Now here, we're going to use the fact that the supremum of A is an upper bound of A. So because of that, that means every element of A is less than or equal to the supremum of A. So in particular, x is less than or equal to the supremum of A. But since M is the maximum of the supremum of A and supremum of B, we know that both the supremum of A and the supremum of B are less than or equal to M. Right? Basically, the supremum of A and the supremum of B are elements of the set, so they must be less than or equal to the largest element of the set. So yeah, supremum of A is less than or equal to M, right? Just because M is the maximum. So this shows x is less than or equal to M. And so, we're done. This completes case 1. Now we're going to do case 2. We're going to consider the case where x is an element of B. Really similar to case 1. Instead, x is going to be less than or equal to the supremum of b. The reason why is because supremum of b is an upper bound of b. So every element of b is less than or equal to the supremum b. So in particular, x is less than or equal to the supremum of b. But then since m is the maximum of supremum of a and supremum b, we know that they are both less than or equal to m. Right? So supremum of b is less than or equal to m. So this shows x is less than or equal to m. And so we're done. No matter what, we have x less than or equal to m. So this shows, given any x in the union of a and b, we have x less than or equal to m. So we can say, for all x in the union of a and b, x is less than or equal to m. And that shows m is an upper bound of the union of a and b. Now we want to show m is the least upper bound of the union of a and b. So we want to verify that second condition. Now the way we're going to do it here is we're going to show for every real number u prime, if u prime is an upper bound of the union of a and b, then m is less than or equal to u. Right? We haven't really used that version yet, so we're going to use it now. So let u prime be an arbitrary real number such that u prime is an upper bound of the union of a and b. From here, we want to show m is less than or equal to u prime. And to show that, well, here's the thing. If u prime is an upper bound of the union of a and b, you can visualize a and b on a number line, maybe, right? U prime is greater than or equal to every element in the union of a and b. So u prime must be greater than or equal to every element in a and greater than or equal to every element in b. Right? It just makes sense. Let's show that first, right? That's going to be useful. So to do that, well, how do we show u prime is an upper bound of a? We would want to show for every x in a, x is less than or equal to u prime. So instead of calling it x, I'm going to call it y. So given y is an element of a, well then y must be an element of the union of a and b. Remember, since u prime is an upper bound of the union of a and b, well then every element of the union of a and b is less than or equal to u prime. So in particular, y is less than or equal to u prime. So that's it. This shows if y is any element of a, then y is less than or equal to u prime. So u prime is an upper bound of a, right? Thus, u prime is an upper bound of a. A similar argument shows u prime is an upper bound of b. So now, we go to the second part of the definition of supremum of a and supremum of b. Remember, from the second definition of this, every upper bound of a is greater than or equal to the supremum of a. Or in other words, the supremum of a is less than or equal to every upper bound of a. Supremum of b is less than or equal to every upper bound of b. So we must have that the supremum of a is less than or equal to u prime. Supremum of b is less than or equal to u prime. So then, remember, we're trying to show m is less than or equal to u prime. But the thing is, m is an element of this set. M must be equal to either supremum of a or supremum of b, right? The maximum element of a set is an element of the set itself, right? M has to be equal to one of these guys. No matter which one it's equal to, we see m is less than or equal to u prime. And so we're done. So putting this all together, we see if u prime is any upper bound of the union of a and b, then m must be less than or equal to u prime. That verifies the second condition of the supremum of a set. So m is the supremum of the union of a and b. And so that's it. This completes this example problem. Let A be a subset of B, which is a subset of the real numbers, where A is not empty and B is bounded above. prove that the supremum of A is less than or equal to the supremum of B. Now, it's clear that the supremum of A and the supremum of B both exist, right? From the fact that B is bounded above, it follows that A is bounded above. From the fact that A is non-empty, it follows that B is non-empty. Right? Let's see why that's true. First of all, if A is non-empty, we can choose some element x naught in A. Since A is a subset of B, x naught belongs to B, and so B is non-empty. Right? So B is non-empty and bounded above. So by the completeness property of real numbers, supremum of B must exist. So then why is A bounded above? Well, since B is bounded above, that means B has an upper bound, right? So there exists a real number u such that for all x in B, x is less than or equal to u. Well, then we can show for every x in A, x is less than or equal to u. Because if we consider an arbitrary element x in A, well, then it follows x is an element of B, because A is a subset of B. Well, since every element of B is less than or equal to u, it follows that x is less than or equal to u. So we see if x is any element of A, then x is less than or equal to u, and therefore, for all x in A, x is less than or equal to u. So u is an upper bound of A, and that proves A is bounded above. So since A is non-empty and bounded above, by the completeness of R, the supremum of A exists. So now, we're going to prove that the supremum of A is less than or equal to the supremum of B. Now, I guess it would be nice if we were to justify in our work why the supremum of A and the supremum of B exist, but I kind of just explained that, so I'm not actually going to write it down. Let's just show, assuming we know that these exist, let's show this guy is less than or equal to this guy. I'm just going to write, note both supremum of A and supremum of B exist. Now, how do we show the supremum of A is less than or equal to the supremum of B? Well, one idea is we show that the supremum of B is an upper bound of A. Because if we show that, well, then supremum of A is the least upper bound of A, right? Supremum of A is less than or equal to every upper bound of A. So in particular, supremum of A would be less than or equal to supremum of B, and we would be done. That's it. So we will show that the supremum of A is an upper bound of A. To show that, we want to show for every x in A, x is less than or equal to the supremum of B. So let's give ourselves an arbitrary element x in A. Well then, since A is a subset of B, it follows that x is an element of B. But then, x is going to be less than or equal to the supremum of B. Right? We know supremum of B is an upper bound of B. So every element of B is less than or equal to the supremum of B. So in particular, x is less than or equal to the supremum of B. So putting this all together, we see if x is any element of A, then x is less than or equal to the supremum of B. So we've shown for all x in A, x is less than or equal to the supremum of B. So that shows the supremum of B is an upper bound of A. And so now, by definition of the supremum of A, the supremum of A is less than or equal to every upper bound of A. So in particular, the supremum of A must be less than or equal to the supremum of B. And so we're done. That's exactly what we wanted to prove. So that's it for this example problem. Let S be a non-empty subset of real numbers that is bounded below. And let C be a real number less than 0. Let CS be the set of all real numbers of the form C times X, where X is an element of S. Prove that the supremum of CS is equal to C times the infimum of S. Now, since S is non-empty and bounded below, we know that S has an infimum. So the infimum of S that we have here makes sense. So we're trying to prove that the supremum of this set is precisely C times the infimum of S. And so we're going to prove that from the definition of the supremum, right? So first off, to prove that the supremum of this set is C times the infimum of S, we first want to show C times the infimum of S is an upper bound of this set. So to do that, we want to show for every y in CS, y is less than or equal to C times the infimum of S. So let's let y be an arbitrary element of CS. Well then, y is C times some element in S. So y is equal to Cx for some x in S. Now since x is an element of S, let's go to the definition of the infimum of S. The infimum of S is a lower bound of S, which means every element of S must be greater than or equal to the infimum of S. So in particular, x is greater than or equal to the infimum of S. But then, since C is less than 0, if we multiply C on both sides of the inequality, that flips the sign of the inequality. So we get Cx is less than or equal to C times the infimum of S. And Cx is y, right? That's what we have here. So y is less than or equal to C times the infimum of S. So this shows if y is any element of CS, then y is less than or equal to C times the infimum of S. And that tells us C times the infimum of S is an upper bound of CS. So we've shown that C times the infimum of S is an upper bound of CS. So the next step to showing that it's the supremum of CS is to show that it's the least upper bound. So we're going to show if U prime is any upper bound of CS, then C times the infimum of S must be less than or equal to U prime. So let's give ourselves an arbitrary upper bound, U prime of CS. From here, we're going to show C times the infimum of S is less than or equal to U prime. Now, how should we do that? We probably need to somehow take advantage of the fact that the infimum of S is the greatest lower bound of S, right? Because we've already used the fact that the infimum of S is a lower bound of S, right? We already used that right here. So we're going to be using the second part of the definition of the infimum of S, which is that the infimum of S is greater than or equal to every lower bound of S. So in particular, what lower bound of S should we be applying it to? Well, here's the thing. U prime is an upper bound of CS. So U prime is going to be greater than or equal to every element, basically every element of the set. So everything of the form Cx where x is an element of S. But as you can imagine, if we divide C on both sides, well, since C is less than 0, that flips the sign of the inequality. U prime over C will be less than or equal to x. X is some element of S. It makes sense to try to show that U prime over C is a lower bound of S, right? We should be able to show every element of S greater than or equal to U prime over C. And hence, that would prove U prime over C is a lower bound of S. So let's try to show that. To do that, we would give ourselves an arbitrary element of S. I will call it Z. We're trying to show Z is greater than or equal to U prime over C. Well, let's see. Right? So we have Z is an element of S. Therefore, C times Z is an element of CS. And since U prime is an upper bound of CS, every element of CS is less than or equal to U prime. So CZ is less than or equal to U prime. But then dividing C on both sides, that flips the sign of the inequality. And so that will give us Z is greater than or equal to U prime over C. So this shows if Z is any element of S, it follows that Z is greater than or equal to U prime over C. So U prime over C is a lower bound of S. So then what do we do with this? Well, since the infimum of S is the greatest lower bound of S, it's greater than or equal to every lower bound of S. So in particular, the infimum of S is greater than or equal to U prime over C. So then we just multiply c on both sides. That'll flip the sign of the inequality since c is less than 0. We get c times the infimum of s is less than or equal to u prime. And that's it. We're done. We have shown if u prime is any upper bound of cs, then c times the infimum of s is less than or equal to u prime. So in other words, we have shown that c times the infimum of s is less than or equal to every upper bound of cs. That's the second condition for c times the infimum of s to be the supremum of cs. So we've proven that it is the supremum of cs. And that's it. That completes this example. Let A and B be non-empty subset of real numbers that are bounded above. Let the set A plus B be the set of all real numbers of the form A plus B, where A is some element of A, B is some element of B. Prove that the supremum of the set A plus B is equal to the supremum of A plus the supremum of B. Right, since A and B are non-empty and bounded above, their supremums exist. So now we're trying to show that this set, we're trying to show that the supremum of this set is precisely this value. And we'll prove that from the definition of the supremum. So to do that, we first want to show that supremum of A plus supremum of B is an upper bound of A plus B. So we want to show for every x in A plus B, we have that x is less than or equal to the supremum of A plus the supremum of B. So to do that, let's give ourselves an arbitrary x in A plus B. Well, then this means x is of the form A plus B, where A is some element of A, B is some element of B. Now, we're going to be using the fact that the supremum of A is an upper bound of A, supremum of B is an upper bound of B, right? Since the supremum of A is an upper bound of A, that means every element of A is less than or equal to the supremum of A. So in particular, A is less than or equal to the supremum of A. Similarly, since supremum of B is an upper bound of B, every element of B is less than or equal to the supremum of B. So B is less than or equal to the supremum of B. And now we're able to take these two inequalities and add them together, essentially, right? In general, when you have A less than or equal to B, C less than or equal to D, it follows that A plus C is less than or equal to B plus D. So using this result, this inequality and this inequality tell us A plus B is less than or equal to the supremum of A plus the supremum of B. And A plus B is equal to X. So X is less than or equal to the supremum of A plus the supremum of B. So putting this all together, we have shown given any X in A plus B, it follows that X is less than or equal to the supremum of A and supremum of B. And so that proves the supremum of A plus the supremum of B is an upper bound of A plus B. Now we want to show the supremum of A plus the supremum of B is the least upper bound of A plus B. Right? We want to verify the second condition for supremum of A plus supremum of B to be the supremum of A plus B. Right? So we're going to show given any upper bound U prime in A plus B, it follows that the supremum of A plus the supremum of B is less than or equal to U prime. So now we want to show that the supremum of A plus the supremum of B is less than or equal to U prime. So then how should we do that? We need to somehow, right, because in the first part, we took advantage of the fact that supremum of A is an upper bound of A, supremum of B is an upper bound of B. Well, now we're probably going to want to somehow take advantage of the second part of the definition of supremum of A and supremum of B, right? The fact that supremum of A is smaller than any other upper bound of A, supremum of B is smaller than any other upper bound of B. Well, maybe, since we're trying to show that supremum of A plus the supremum of B is less than or equal to U prime, if this is what we're trying to show, then that would amount to showing the supremum of A is less than or equal to U prime minus the supremum of B. And to show this, we would just have to show that u prime minus the supremum of b is an upper bound of a. Because if u prime minus the supremum of b is an upper bound of a, well then the supremum of a is less than or equal to every upper bound of a. So this would follow. So that's all we have to show. We're going to show u prime minus the supremum of b is an upper bound of a. To do that, we give ourselves an arbitrary element of a. I'll call it y, and we'll show y is less than or equal to u prime minus the supremum of b. Now, after spending some time on my own trying to figure out a way to do it this way, I couldn't figure out a way. So we're going to change our approach. Instead of letting u prime be any upper bound of a plus b and showing that the supremum of a plus the supremum of b is less than or equal to u prime, we are going to let u prime be a real number less than the supremum of a plus the supremum of b, and prove that u prime is not an upper bound of a plus b. So from here, we'll show u prime is not an upper bound of a plus b. Because if we do that, well then we have supremum of a plus supremum of b is an upper bound of a plus b, but then anything less is not an upper bound of a plus b. So that proves supremum of a plus supremum of b is the least upper bound of a plus b, and hence it's the supremum of a plus b. So how do we show u prime is not an upper bound of a plus b? We want to find an element in a plus b such that u prime is strictly less than that element. So here's the idea. We just subtract supremum of a to the other side. We get u prime minus the supremum of a is less than the supremum of b. So what we see here is u prime minus the supremum of a is strictly less than the supremum of b. Therefore, u prime minus the supremum of a is less than the least upper bound of b. So anything smaller than the supremum of b is not an upper bound of b, right? So u prime minus the supremum of a cannot be an upper bound of b, right? This just comes from the definition of the supremum. Anything smaller than the supremum of b is not an upper bound. So u prime minus the supremum of a is not an upper bound of b. And since u prime minus the supremum of a is not an upper bound of b, what does that mean? It means u prime minus the supremum of a is strictly less than some element in b, right? U prime minus the supremum of a can't be greater than or equal to every element of b. Instead, it must be strictly less than some element in b. Call it b naught. So that's what we get, but then let's just subtract b naught to the other side, add the supremum of a to the other side. You get u prime minus b naught is less than the supremum of a. So what we see here is u prime minus b naught is strictly less than the least upper bound of a. Anything smaller than the supremum of a is not an upper bound of a, by definition of the supremum. So in particular, u prime minus b naught is not an upper bound of a. Which means u prime minus b naught must be strictly less than some element of a. I'll call it a naught. But then we just add b naught to the other side. So we see u prime is less than a naught plus b naught. And a naught plus b naught fits the form to be an element of a plus b. So this is an element of a plus b. We see that u prime is strictly less than some element in a plus b. And that's it. That shows that u prime is not an upper bound of a plus b. And so, putting this all together, we see if u prime is any real number less than the supremum of a plus the supremum of b, then u prime is not an upper bound of a plus b. And that was the last condition we wanted to verify. So we have supremum of a plus supremum of b is an upper bound of a plus b, and anything smaller is not an upper bound of a plus b. So by definition, supremum of a plus supremum of b is the supremum of a plus b. And that completes this example problem. So now we're going to look at one more example problem for this video. Let S be a subset of the real numbers and let U be a real number. Prove that U is the supremum of S if and only if, for every positive integer n, U minus 1 over n is not an upper bound of S, and U plus 1 over n is an upper bound of S. So, to prove this, we're trying to prove a statement containing if and only if. So we're going to prove if U is the supremum of S, then this is true. And then we're going to prove if this is true, then U is the supremum of S. Let's start out by proving the forward. We will suppose that U is the supremum of S. From here, we want to prove that this statement is true. And since we're trying to prove a statement about every positive integer n, let's give ourselves an arbitrary positive integer n. From here, we want to show U minus 1 over n is not an upper bound of S. U plus 1 over n is an upper bound of S. So how should we show U minus 1 over n is not an upper bound of S? We want to show that U minus 1 over n is strictly less than some element in S. So how do we do that? Well, the idea is U minus 1 over n is less than U, or in other words, U minus 1 over n is less than the supremum of S. So actually, from the definition of the supremum, anything smaller than the supremum of S is not an upper bound of S. So U minus 1 over n is not an upper bound of S. So actually, we didn't need to show that U minus 1 over n is strictly less than some element of S. We actually ended up deducing U minus 1 over n is not an upper bound of S without having to refer to the definition of an upper bound. We actually referred to the definition of the supremum to obtain this. So we're all good there. Now we want to show that U plus 1 over n is an upper bound of S. Here we will refer to the definition of an upper bound. So we want to show for every x in S, x is less than or equal to U plus 1 over n. So let's give ourselves an arbitrary x in S. Actually, we'll be able to show this pretty quickly. So instead of saying let x in S be arbitrary, I'm just going to say if x in S is given or arbitrary, well then, since the supremum of S is an upper bound of S, every element of S is less than or equal to the supremum of S. So x is less than or equal to the supremum of S. In other words, x is less than or equal to U. And U is less than U plus 1 over n. So this shows we have x is less than U plus 1. This shows x is less than U plus 1 over n. So x is less than or equal to U plus 1 over n. So this shows if x is any element of S, x is less than or equal to U plus 1 over n. So U plus 1 over n is an upper bound of S. So that's it. This proves if n is any positive integer, we have U minus 1 over n is not an upper bound of S, U plus 1 over n is an upper bound of S. That's what we have just shown here. So that proves the forward. Now we're going to prove the converse. To prove the converse, we suppose for every positive integer n, U minus 1 over n is not an upper bound of S, U plus 1 over n is an upper bound of S. From here, we want to show that U is the supremum of S. And we're going to show U is the supremum of S using the definition of the supremum. So first, we want to show that U is an upper bound of S. So we want to show for every x in S, x is less than or equal to U. So let's give ourselves an arbitrary x in S. From here, we want to show x is less than or equal to U. Now, what we're going to do here is we're going to assume for a contradiction x is greater than U. Because, as you can imagine, if we walk any distance to the right of U, right? If we're any bigger than U, we will basically, if we imagine U on the number line, if we walk anywhere to the right of U, eventually we should encounter x, but in between there, we should encounter something of the form u plus 1 over n. Now, x is an element of S, u plus 1 over n is an upper bound of S. So that means x would have to be less than or equal to u plus 1 over n, but we see x is greater than u plus 1 over n, according to our diagram. So we should be able to reach a contradiction. So then how do we reach that contradiction? We should be able to choose something like x greater than u plus 1 over n greater than u, right? There should be some positive integer n which satisfies this, right? We ultimately care about this one, though. So then, if we isolate n, what does this look like? We have x minus u greater than 1 over n, and since x is greater than u, x minus u is positive. So dividing x minus u to the other side, multiplying n to the other side, we have n greater than 1 over x minus u. N is a positive integer, bigger than 1 over x minus u. So what we're going to do is we're going to invoke the Archimedean property. So we choose a positive integer n such that n is greater than 1 over x minus u. Well, then from here, we should be able to take this inequality and obtain x is greater than u plus 1 over n. Because what do? We would multiply x minus u to the other side, divide n to the other side, but then we could add u to the other side, we get x is greater than u plus 1 over n. But then, by our hypothesis, we know that u plus 1 over n is an upper bound of S. And that means every element of S is less than or equal to u plus 1 over n. So in particular, x is less than or equal to u plus 1 over n. So we see x is greater than u plus 1 over n, and x is less than or equal to u plus 1 over n, so we've reached a contradiction. Our assumption that x is greater than u led us to a contradiction, so we must instead have that x is less than or equal to u. And now putting this all together, we have shown if x is any element of S, then x is less than or equal to u. So for all x in S, x is less than or equal to u. And that means u is an upper bound of S. Now, we want to show u is the supremum of S, the next step is to show, given any real number u prime, if u prime is less than u, then u prime is not an upper bound of S. So, let's give ourselves an arbitrary real number u prime less than u. We're trying to show u prime is not an upper bound of S. So, to show that, what we can do here is we can try to find something like u prime less than u minus 1 over, I'll say m, less than u. Right, if we walk anywhere to the left of u, we should be able to find a real number of this form, u minus 1 over m, where m is some positive integer, right? And we can find one to the right of u prime as well, right? Now, what we ultimately care about is this, right? So if we isolate m on both sides of this inequality, what would that look like? Well, if we add 1 over m, subtract u prime, we get 1 over m is less than u minus u prime. Now, u minus u prime is positive because u prime is less than u. So if we divide u minus u prime to the other side, multiply m to the other side, we see m is greater than 1 over u minus u prime. So we just have to choose a positive integer m such that m is greater than 1 over u minus u prime. We can do that by the Archimedean property. So then we can show from here that u prime must be less than u minus 1 over m. Because if we multiply u minus u prime to the other side, divide m to the other side, we get u minus u prime is greater than 1 over m. So then adding u prime to the other side, subtracting 1 over m to the other side, we get u prime is less than u minus 1 over m. Now, by the hypothesis, so why is this important? Because u minus 1 over m is not an upper bound of S. Right? According to the hypothesis, u minus 1 over m is not an upper bound of S. Which means u minus 1 over m is strictly less than some element of S. And I'll call that element, I don't know, Q naught. But then we see u prime is less than u minus 1 over m, and u minus 1 over m is less than Q naught. So u prime is less than Q naught. So we see u prime is strictly less than some element of S. That shows u prime is not an upper bound of S. Which means, since u prime is not an upper bound of S, that's it. We're done. We have shown if u prime is any real number less than u, then u prime is not an upper bound of S. That's the last condition we need to verify for u to be the supremum of S. And so we're done. Therefore, u is the supremum of S. And so that's it. That completes this example problem. And so that is pretty much it for this video.